Hello dear students, in this video we are going to learn about ensemble learning. Until now in machine learning you might have learned many classification algorithms, say for example logistic regression, naive Bayes, KNN. In all this classification algorithm we will be having only one model and then we will be giving our data set as an input to the model and finally we will be getting the output. In many of the times, what is the problem here is it leads to high variance. We are going to another approach in machine learning called ensemble learning. So what is this ensemble learning is rather than having only one classifier, we are going to have some collection of classifier here. And finally, from all this collection of classifier, we are going to apply the voting concept. And then from that, we are going to take the decision. So that is what actually happened in ensemble learning. And in ensemble learning, there are many different approaches available or many different techniques available. Say for example, bagging, boosting, stacking and all. So here we are going to concentrate on bagging as well as boosting. So first let us discuss about bagging. So in bagging, we have an algorithm under bagging that is called as random forest. So what is this random forest is? It is an advanced version of bagging. In random forest, so here from the name itself, you can understand two terms are there, random and the forest. So why it is called as forest means in random forest, we are going to use multiple number of decision trees. So you might have learned about decision tree already. So here we are going to use multiple decision tree. So that is why we call it as forest. And why we call it as random is we are going instead of giving the complete data set as the input to this decision tree, we are going to use a random sampling of the data set. And also we are going to use feature sampling to create input to this individual decision trees. So here we can say the random forest is going to use parallel learning process. Okay, it is going to use parallel learning process. So let us discuss how it is going to be act as parallel learning process. Let us take a sample data set. Consider I'm going to have a data set with features x1, x2, x3, and x4, which may contain some sample instances like s1, s2, s3, s4, s5, and like t1, t2, t3, t4, and t5. Let it be u1, U2, U3, U4, and U5. And the output classes maybe let us, okay, here also we will give one more, V1, V2, V3, and V4. And the final output classes may be 0 or 1. Okay, so this is our data set. And here we have set in random forest, we are going to create multiple decision trees. So how to this multiple decision trees, we want to give input, right? So to give the input, we are going to use random sampling of the instance as well as we are going to use feature sampling. Feature sampling, how we are going to do is, for example, here you can see there are 4 features. So how we are going to do sampling on the feature is, you can make use of the square root or you can take the log of it. So let us take a square root of it. Since we have 4 features, so the square root of 4 is 2. So we are going to take 2 features as a subset of this. So say for example, for the first subset, we are going to take feature x1 as well as x3, and we are going to also use instance or we are going to randomly choose some instances as well. Say for example, x1 t1, s3 t3, and s5 t5, like that. Okay, so this is one of the subset of our data set. And let it be the next one be x1 and x4, and that also have some instances in it. Okay, and let us have one more like x2, x3, maybe the next set of subset of the data. Okay, so this, let us consider this as these are our subsets. So for this subset of our original data, will be creating our decision tree. Say for example, for the first subset of the data set, say for example, this is our data set D, and this is our data set DJ. Okay, so so these are the subsets. So for this, let us have a decision tree like this, and for this subset, we may be creating a decision tree like this. And for this subset, we may have a decision tree like this. Okay, so here you can see these are our collection of decision trees. So that is why we call it as forest, since we have more than one decision tree. And this process, what we are going to do here is, right, this process is called bootstrap. Okay, so to do the bootstrap from the original data set, we are going to do some row sampling as well as some feature sampling, and we got this. For each of this, we are going to do some, we are going to create the decision tree. You may know how we will be creating a decision tree. Probably we can use an entropy, and using the entropy, we will be using information gain, and who have the highest information gain, that will become the root node. So this can be one of the feature. And further, we will be subdividing into many another level, and until and in the classes will be in the leaf node. We know how to create the decision tree. Similarly, here we have another decision tree for all the three. So the number of decision tree which we going to create, we can decide on it. And finally, we are going to aggregate the result. Say, for example, when a new input comes, for example, I'm going to say when S6, T7, and U8, V5, maybe the input feature, okay, input sample coming over here. So for this, we want to find what will be the result. So will it belong to 0 class or it belong to class 1? So we have to decide on it. So we'll be giving this input data points to all of this decision tree. And for example, the first decision tree is going to create the output as 0. And the second decision tree may be creating output as 1. And the third decision tree may also create an output as 1. So what we will be doing is, we will be taking a majority voting. So the decision tree 2 and the decision tree 3 have given the output as 1. So the majority is 1. So output will be 1. So this process is called aggregation. So this is what will be this is what happens in the random forest. Okay, so as I said, we will be creating multiple decision tree. To create this multiple decision tree, we'll be having row sampling as well as the feature sampling, and we will be doing parallel learning process. What is parallel learning process? One decision tree doesn't depend on other decision tree. So we can parallelly create multiple decision tree, and we'll be parallelly giving this input to all this decision tree, and we will be getting the output. So this is what happens in the random forest. So, so this is the first technique in ensemble learning. The next technique in ensemble learning is boosting. So, as we saw here in random forest, it is a parallel processing or parallel learning process, right? But this boosting, the next is boosting. Under boosting, if you see, it is a sequential learning process, which means, for example, this is also another ensemble learning method only. But here, if, for example, if we have one classifier, for example, classifier 1, classifier 2, and classifier 3. Each of this classifier depending on one another. For example, classifier 1 will be given the complete data set, Okay, and we will be creating a model here, and this second model will be depending on the first model. Okay, and the third one will be depending on the second one. So that is why it is called a sequential learning. It is not parallel learning. Here we will be learning, doing sequential learning. So so that is what given here in banking. Every model is independent on each other. But in boosting, since it is a sequential model, one model is depending upon its previous one. So how we will be doing this boosting is, we will be making a model from the training data set. From the original, we will be making this model, and the second model will be depending upon the first model with the attempt to correct the errors which occurred in the first model. So that is, and the third model will be correcting the errors occurred in the second model. And probably fourth one model will be correcting the error will in the third model. So that is, so everyone will be depending upon its previous model. And finally, aggregating this, we will be getting a good, perfect classifier. So that is what boosting is. So one of the example of boosting is AdaBoost. So which means adaptive boosting. So this is one of the algorithm of boosting. So how does this boosting, adaptive boosting performance? For example, let us consider a data set here. So which have some features like gender, age, income, and illness. So illness is our output class. So by saying this, we can say whether they have illness, yes or no. So initially what we'll be doing is, by seeing this complete training data, we will be creating a classifier. So, and so here you can see, in random forest, we will be creating a complete decision tree in each and every model, right? So here what happened is, we will be creating a decision stump, which is like, for each of the feature, we will be creating, for example, this is the initial data set, right? So for each of the features, we will be creating a decision stump, which means it will be having only one level. We have the root and the next level. Only this much will be there. And so each of the feature will be creating, this is called a stump. It is not a complete decision tree. So it will be having this level, a root and one level of it. So for this, we will be calculating the Gini index for each of the tree. So each stump will be for each and every feature for the data set, and which stump having the lowest Gini index, that will be chosen as our first stump. Okay, so that is what happened here. So initially what we'll do is, for each of this instances, we will be assigning some random weight. So here you can see, we are going to assign some random weight. Initially, we don't know what weight we can assign to all these instances. So we are going to, since there are only 5 records, we are going to equally distribute the weight for all the samples, so that we put 1 divided by 5. For example, if I have 10 features, we'll be equally assigning the weight. So it will be like 1 divided by 10, 1 divided by 10, like that. So this is the first step. So after we assign it, we will be given it to the model, and then we will be finding the error. So how will be finding the error is, for example, consider if the fourth one is wrongly classified. Actually, the output of this is yes. If it is classified as no, so then it is wrongly classified, right? So for example, if one more is wrongly classified, means what does it do is, the total error is the summation of all the sample weight. So it will be summing up these two weights, 1 divided by 5 plus 1 divided by 5. That is what happened. The total error is the summation of the sample weight of the misclassified data point. So these two are misclassified. So those weight will be summed up. So, and that is what happened as the next step. So here, let us consider, in this example, let us consider this is wrongly classified. Okay, only the sample 4 is wrongly classified. So what does it do is, it will be calculating the performance of the stump. So here, as I said, a stum will be created, and it is not a complete decision tree. Root node with one level for every feature will be created. So for this stum, the performance of the stum will be created. The formula is this. In this case, as I said, we are considering that only the fourth sample went wrong, right? So the total error is, if we have more than one, we will be summing up all the errors. Since we have only one error in this case, so the total error will be 1 divided by 5. So 1 by 2 log 1 minus the total error here is what? What is the weight of it? 1 divided by 5. For example, if I have more than one error means, what will we do? We will be summing up all these things, right? So here, when we apply on this formula, we will be getting the performance of the stum as 0.69. After we get the performance of the stum, then we have to what happened next is, so for the wrongly classified samples, we have to increase the weight, and for the correctly classified instances, we have to decrease the weight. To do so, we have a equation like this: new sample weight equal to old weight into exponential of plus or minus amount of say, which means the performance of the stum. So, for example, here only the fourth index went wrong, right? For the fourth index alone, we will be increasing the weight. For the rest of the things, we will be decreasing the weight. So, as I said here already, so we know that so every classifier will be depending on the previous one, right? So one classifier will be depending upon the previous classifier. So how does this? If the first classifier makes some error, the error instance will be given the higher weight, and correctly classified instances will be given less weight. So that input will be given as the input to the second classifier. And same thing in the second classifier also, if something is wrongly classified, that instance weight will be increased and correctly classified instance weight will be decreased. So here we know this fourth instance is wrongly classified. So that one's weight need to be increased and the other weight will be decreased. So what we do is, this is the formula. And we also have calculated the performance of the stump as well. So when we calculate the new weight, for correctly classified, we want to decrease the weight, right? So here we are applying like old weight is what? 1 divided by 5. So for the fourth instant, what is the old weight? 1 divided by 5. So into exponential of, since we want to decrease the weight, we are going to apply minus, and the value of the performance of the stem, that is 0.69 is given here. And here we are going to calculate the new weight. So the new weight for correctly classified samples are 0.1004. So that is what given here. For all the correctly classified instances, we are giving 0.1004. And for the wrongly classified sample, we have to increase the weight. So here for the exponential, we are going to take the plus symbol. So we got the value. So we got the increased weight, right? So 0.3988. So that is the increased weight. So initially this was the weight. After we calculate the performance of the stem and the new weight, for the wrongly classified sample or the instance, we increase the weight. The remaining we decrease the weight. And then we are going to normalize it so that the sum of all will be giving output of 1. So to normalize it, we are going to divide the weight of all the samples by the total weight. So if you sum up all of this weight, we will be getting 0.8004. So with that, we are going to divide all the weights so that we will be getting a normalized weight. So when you sum up of all, we will be getting a sum of 1. So this is how we will be doing for one. Same thing we want to repeat again and again. So what will you do for the next time? Again, we will be giving this data as an input to the next sample with this updated weight. And then we will be doing the classification by creating the stumps for each and every features. And there we will be again getting some misclassification. For the misclassification, again, we have to calculate the performance of the stump, and then we have to update the weight. So if it is correctly classified, decrease the weight by this formula. And if it is wrongly classified, increase the weight. So we have to repeat it. And finally, we will be, finally, when we aggregate all this, we will be getting a perfect classifier. So this is what happened in the boosting technique. I hope you got it. Now let us see the implementation of this. Okay, wait a minute. Okay, so now first we are going to see the implementation of random forest. So for that, initially I have chosen some, we know the necessary modules are imported, pandas and number is used, and then I'm going to use a predefined already available data set inside the sklearn, that is iris data set. We know what is the iris data set is. So it has some features like sepal length, sepal width, petal length, and petal width. And finally, the output classes, we have three classes. Setosa is there, and then we have vesicolor, as well as we have virginica. So these are the three classes, and this is what the data set we are going to use for this random forest. So we have loaded this, we have imported this iris data set, and I'm loading it in a variable called iris. And then we know usually we want the we want to separate the independent variable and the dependent variable. So the independent variable is taken in the variable x. So iris.data, so that will give our independent data inside the x. So we will be getting sepal length, sepal width, petal length, and petal width will be assigned inside the x. And y will be getting our dependent variable. So that is our target. So this iris variable dot target will give you the dependent variable, that is the response variable. So once we get it, we can split our data into training and testing. So by using this from the sklearn, we are using this train test split, and we are going to split it into 70% is taken for training, and 30% of this data is taken for the testing. So we have the data, this variable is train, x train, and x test is available now as 70-30%. Now we are going to implement this random forest, we are going to use already available random forest classifier, which is available inside the sklearn ensemble module. We are going to directly take it, and we are going to use it. Okay, and we are going to use this function, and we are going to assign it in a variable called model. And inside this random forest, we can apply different parameters. So how we'll be getting what are the different parameters? If you can go and see it in the sklearn, if you go inside sklearn, we will be getting this sklearn's website. If you go inside sklearn, in API, you can see ensemble module will be there. So if you go inside this ensemble, sorry. So here you can see under the ensemble. Okay. So if you search inside the API, you will be finding the ensemble. Under the ensemble, if you see, you can see inside this, if you search under API, we will be having the ensemble. Under the ensemble, we have different ensemble approaches available. Ada boost, bagging, and everything is there. Now we are going to see on random forest classifier. So if you go inside that, you can see the parameters which we can use for this library function of this random forest classifier. So what are the parameters we have is, first is n estimator. What is this n estimator? So as we said, random forest means we have collection of n number of decision tree, right? So here we can see the number of decision tree we can use. So in the version 0.22, it has changed to 100 actually. Earlier it was in the previous version, the default number of tree is 10. In the version it is changed to 100. So here we can change this as we like. So here I have given the estimator, which means the number of decision tree to be created is 30. And then likewise, we can try for the other parameters also, like criteria. So you know that in decision tree we have entropy, which means the impurity. Based on the impurity, we'll be calculating the information gain. And who have the highest information gain, that will become the root node by which we will be creating the decision tree, right? So another one is Gini is another method. Log loss is another method. So you can even say what is the by default Gini is taken for criteria. Okay, and even you can try with Gini. And what is the maximum depth and minimum sample split you can give, minimum sample leaf you can give, maximum features you can take. So as I said, no, if I have 4 features, you can see when you do the feature sampling, how many sample you can choose. So yeah, I told you, like, even you can take square root or log. That also you can, by default, the square root is taken. Even you can change it with log too. So likewise, you can choose this different parameters and try how well your model is going to perform. So now let us take n class n estimator as 30, which means now as of now, I'm taking only the number of decision tree as a parameter, and we are passing here. And then we are going to train it using fit function by passing the x train and y train. So you know what is x train? The independent variable and the dependent variable is given. And then we are going to see the accuracy. So model.score will give you the accuracy. So we, by giving the x test data and we are by giving the y test, the accuracy we get is 97%. And then by giving this x test, and we are going to predict it using the model. The variable we created for this random forest classifier is model. So model.predict, by giving x test, you are going to check how well it is going to predict it. So after we predict it, we are going to see the confusion matrix. So confusion matrix will help us how much is correctly classified, how much is wrongly classified. So as we see in our data set, we have 3 classes. We know that Setosa, vesicular, and Virginica is the 3 classes. So here for the first class, 17 samples are there. All 17 is correctly classified. And then for the second class, 13 is correctly classified and 1 is wrongly classified. And for the third class, 14 samples are there. All 14s are correctly classified as Virginica. So this is our confusion matrix for our model. And then we have plotted using matplotlib. And so here we can see what is a precision, recall, and F1 square for all these 3 classes. And also we are displaying the accuracy of this model. So as I said, even we can able to change the parameter. Now let us try with a different parameter also. Say for example, let us try with this one, max feature. Or even you can try with another one, the criterion. Let us first try with criterion. So here, let me change the second parameter, criterion equal to. So by default, what is the criterion is Gini. Now let us try with entropy. And let us see how what is the change we are getting. So again, I'm going to run this model with this new parameter. And then I'm going to train it. And then I'm going to see the accuracy. So there is no change here. Even you can test it with different number of decision tree also. Even you can try with 40. So you can run it. And after running again, there is no change. You can see with less number of decision tree, and you can see what is the change is coming. It's not giving any change. So you can try with different parameters, and you can see how well it is performing. Okay, and even you can try with different other parameters like max feature. You can try with log2, all this different thing, and depending upon the parameters you choose, that will also show you different output. Okay, so this is about random forest. And the next one we are going to see is AdaBoost. So random forest is a parallel learning method. But in AdaBoost, we know that the first classifier will be giving the complete training data. and the second classifier will be depending upon the first classifier, where it will be correcting the wrongly classified samples, right? And similarly, the third classifier will be depending upon the second classifier. So it is a sequential learning process. We know that. That is the main difference. Here again, we are going to use the same data set and same thing. And here from the sklearn library, we are going to import this AdaBoost classifier. And here also, we are using how many number of estimators we have to use. So say, for example, you can go and see in the AdaBoost classifier. You can see for the AdaBoost classifier what are the different parameters you can have. So the estimator here in the AdaBoost is a base estimator for which the boost ensemble is built. Okay. So we know that here we don't have the complete decision tree. We'll be creating the stems, right? So you can see like that. So you can change the variable on it. And n estimator is the maximum number of estimator we give, and the learning rate is there. By default, the learning rate is 1, and you can use different sample state base estimator, and you can try with different things. So here also, we are giving n estimator as 100, learning rate is 1, and then here we are training it. And when we train it using this parameter, we got the accuracy of 93%. And then we are predicting it, and we are making the confusion matrix, and we can see the precision recall and F1 score. And one more thing I'm going to show you here is, we are going to reduce the error. We can even use logistic regression. So base estimator, if you see here, the base estimator here, default, we are not going to use anything as a base estimator. But we can, the base estimator for which the boosted example is built, we can use for, suppose for sampling weight, you can use different techniques. So here I'm going to show you the base estimator with logistic regression. So for that, we are going to use the basis. For that, first we are going to import the logistic regression, and I'm going to put it in a variable my logistic. And for the base estimator, we are going to use that as an input. So here you can see earlier we have n estimator and learning rate. Along with that, we have added the base estimator as one more parameter. And then we are going to train this AdaBoost classifier. And if you see the score earlier, the score we got is 93%. After we add this base estimator, you can see the improvement. That is, the score got improved, that is 95%. And for that, again, you can see the confusion matrix and the the accuracy. So by changing the parameters of this AdaBoost classifier also, you can see different metrics. Like you can see the different performance in accuracy, in precision, in recall, as well as in the F1 score. So you can try with different parameters. Hope you got it. Thank you, ma'am.